Hello and welcome back to Partial Differential Equations, the video series where we formulate and solve some certain partial differential equations. And indeed, in today's part 3, we still talk about Laplace's equation and we will consider its fundamental solution. This one is also often called the Newtonian kernel because of its application in 3 dimensions. But here we will definitely formulate everything for the general n dimensions immediately. However, before we start with that, as always, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And please don't forget, as a supporter on Steady or Patreon, you can download all the additional material for the videos. For example, you can find PDF versions, books and quizzes. And then without further ado, I would say let's immediately recall Laplace's equation and the results from the last video. So the important ingredient is just the Laplacian in n dimensions, and every solution u we call a harmonic function. Moreover, we already know a lot about solutions defined on the whole space with the exception of the origin, which are also radial symmetric. Namely, depending on the dimension, it's either the logarithm function or a function that looks like 1 over r. And of course, if I say r, we just mean the standard norm of our vector x. So it's the distance from the origin to x measured in the Euclidean norm. So as you can see here, only the dimension 2 is the special case because all the other dimensions can be put into the norm of x to the power 2 minus n. This means changing that to a positive power, we always have the norm of x in the denominator. Okay, so this is the necessary result that we get if we want to have a radial symmetric solution, and this is what we can use to define the fundamental solution. In other words, we will just fix suitable constants c1 and c2. And as you might already guess, a natural choice for the constant c2 would be just 0. However, for c1 this is not so clear, and I will justify the choice for it later on. But first, let's write down the function gamma, which we call the fundamental solution of Laplace's equation. And as already mentioned, sometimes you will see it as the Newtonian kernel. However, there I should already tell you that there is no general consensus about which sign is the correct one for the constant c1. Which just means that some people will say that minus gamma is what we should call the fundamental solution. But since this is not a big issue, we can just ignore it for the moment. So you see here in the first step, for n is equal to 2, I will use minus 1 over 2 pi. In fact, this makes the logarithm function in a small neighborhood around the origin to a positive function. And exactly this is what I want here, and I also want to have it for all the other cases. And now I want to divide by the volume of the unit sphere in Rn. So more precisely, this is the n-dimensional volume of the n-1 dimensional unit sphere. So this is the choice of the constant, but you see I also want to have this positive, so I have to include a minus sign as well. Or to make it simple, I can just exchange n and 2 in the difference here. Therefore, what you should recognize in general is that we have a quite simple choice for the constants from before. We completely ignore c2, and for c1 we put in the volume of the n-1 dimensional unit sphere. But we also choose a minus sign there to make it positive around 0. So please note here that the unit circle S1 has a circumference of 2 pi. And moreover, we also know that the area of the two-dimensional sphere S2 is given by 4 pi. Therefore, in the important three-dimensional case, we have 1 over 4 pi with a plus sign times 1 over the norm of x. So for example, in physics, you might recognize that as the Coulomb potential. But as always, we don't have to restrict ourselves to this case because we can easily deal with the general n as well. Maybe the only problem there is that you don't know the general formula of the n-1 dimensional volume of our unit sphere. However, there I can tell you that this one can be calculated by using the gamma function. And fortunately here, the gamma function is denoted by a capital gamma. And we need it at n halves plus 1. And the inverse of that is multiplied by n and pi to the power n over 2. In fact, one can simplify this formula even more, but for us it's already good enough that we know that the surface area of the unit sphere, so the n-1 dimensional volume, is fixed by this formula. So you can remember, it's the generalized surface area, and the radius of the sphere is fixed by 1. Very well, now you know the whole definition of the so-called fundamental solution of Laplace's equation. However, we didn't discuss at all why we actually call it fundamental, but this is something we will do in the next videos. Here I first want to focus on some simple properties this function gamma has. For example, it's not defined at 0 at all, and it actually has a singularity there. This means if we look at the graph of gamma around 0, it explodes there. Hence, if we get closer and closer to the origin, our values of gamma of x will get bigger and bigger. So obviously the limit x to 0 is infinity in all cases. So please note, this is the choice of the sign we made before. But now the good thing about this singularity is that it is not too bad, because the function still stays integrable around it. This means such an integral that goes over the singularity still has a finite value. And in fact, this is quite an important part of a fundamental solution. Therefore, we should definitely formulate this result as a proposition. And since we just want to talk about the singularity, which is at the origin, we can just take a ball centered at 0. And indeed, we can keep it simple by just taking the unit ball. So we have an n-dimensional integral in Rn, and the unit ball I denote by b10. And now integrating gamma x dx will give us a finite value. However, the explicit value we get out will depend on the dimension n. For example, for n is equal to 2, we get out 1/4. And for the other cases, we have 1 over 2 times n minus 2. So the result is different in different dimensions, but you should note that we always get out a positive number. This is quite clear because this is how we chose the sign for gamma. And now in order to prove it, we just have to calculate an n-dimensional integral. So this should not be too complicated. And in fact, we can use the radial symmetry of gamma to integrate with polar coordinates. This just means that we can split the integration into two parts. The first part is with respect to the radius, and there we have the factor r to the power n minus 1. And the second part is just the surface integral over the unit sphere of dimension n minus 1. And there the surface element we just call d sigma and the variable omega. So you see, we just have some change of variables for our function gamma. Namely, now we have to integrate gamma of r times omega. And with that we have it. This is the standard formula for the integration in polar coordinates in n dimensions. And if you don't know that one, then please check my multidimensional integration course for a whole explanation of this formula. Because here I just want to apply it, and as you can see, it works really nicely in our case. Indeed, we have the symmetry in gamma, which means it does not depend explicitly on omega. So as a reminder, here in the two-dimensional case, we just have the logarithm of r. And on the other hand, in the higher dimensional cases, we have r to the power 2 minus n. So by the definition of gamma, the direction on the unit sphere does not matter at all. So in both cases, the surface integral here can be solved immediately. Namely, what we get is just the generalized surface area of our unit sphere. So in the first case, this means we have the volume of S1. And as discussed before, this should immediately cancel with our factor 2 pi there. So the only thing we have to integrate here is r times the logarithm of r. And now you should recall your real analysis knowledge, because r times the logarithm of r is actually a bounded function on the interval from 0 to 1. So for example, for calculating the limit going to 0, you can use L'Hopital's rule to show that this limit exists. And this immediately implies that the integral definitely exists, it's a finite value, but we can also find it by using an antiderivative of this function. Indeed, this is usually done by integration of parts. But I just show you the result because here you can immediately check that this is correct. And afterwards we can just use it, which means we put in 0 and 1. And then finally the last limit process just gives us 1/4. And indeed, this is what we have already stated before. And in fact, the second case is even easier to solve. Simply because there we just have a power of r to integrate. And now as before, let's do a similar thing, which means first using our polar coordinates to get this factor in. And then after that we have our gamma function and then the surface integral, which we can immediately solve. Which also implies that this volume here cancels with the factor we have chosen before. And then obviously the only thing we have to do to solve this integral is to combine the two powers of r. And this is quite nice because you see what we get here is just r to the power 1. So definitely a one-dimensional integral which we can immediately solve. So we just get 1/2 times our factor 1 over n minus 2. So as expected, we get out a positive number, but most importantly here is that we have a finite number for the whole integral. So please keep that in mind. We have a singularity in gamma, but in the integral, the high dimension we have kills it. In fact, the convergence of this integral is really important and we will use it in the next videos. So I really hope I meet you there again and have a nice day. Bye bye.